Hello students, let us begin with another topic of the fourth module here. Uh, the topic name is linear arrays of anisotropic point sources of equal amplitude and spacing here. So in the previous cases, what you have learned here is we have learned 5 cases here. Case number 1, where we have learned regarding the 2 point sources of equal amplitude and same phase here. And in the second case, we have learned 2 point sources of equal amplitude and phase difference was there. That is out of phase was there. In the third case, equal amplitude and quadrature phase. Fourth case, equal amplitude and any phase was there. In fifth case was any amplitude and any phase difference was there. These were the 5 cases which we have learned here, considering only the 2 point sources here. Now let us consider n isotropic point sources which are having the equal amplitude and the spacing here. Okay, so you can see this particular figure here. In the x-axis you can see here, that is point source 1, point source 2, point source 3, 4, 5, 6, so on up to there are n isotropic point sources are there here, which are separated with the equal distance here. It means the distance between the adjacent point sources are equal here. So that has been represented by a small t here. Okay, and let us consider a case where isotropic point sources of equal amplitude spacing are arranged linearly here. Okay, linear fashion it has been arranged here, as it has been shown in the particular figure, where n is any positive integer here. So what is exactly the total field that we are going to get at large distance in the direction of a pi here? So that we have to calculate here. So you can see in this particular figure here, phi is equal to 0 is there, and here phi is equal to 90 is there. So in the at a distance point, okay, phi, we have to calculate the total field that is being generated by these n number of isotropic point sources here. So considering that one, we have a equation number 1 here. E is equal to 1 plus of e raised to j psi plus e raised to j2 psi plus e raised to j3 psi, so on up to e raised to j n minus 1 psi here. I'll let you know how exactly this particular equation number 1 came into picture here. So here psi is nothing but here total phase difference here. Total phase difference of the fields from adjacent sources here. Okay, so this is the phi here, and it has been given as 2 pi psi is equal to 2 pi d divided by lambda cos phi plus delta here. That will also be written as dr cos phi plus delta here. This is what is delta, is the phase difference here. Phase difference between what here adjacent sources here. Okay, remember here delta is the phase difference and the psi is the total phase difference here. Okay, now what we have considered or assumed here is, whatever the phase reference is, that phase reference would be taken as the origin here. That is, at the origin we are having only point source 1 here. So point source 1 will be taken as the phase reference here. So if at all we consider point source 1 as the phase reference, then we'll be having one only here, amplitude. We will not be having any phase reference here. Okay, not any phase difference here. Okay, so if at all I consider the point source 2, that value will be e raised to j psi here. We'll be having certain phase difference from 1 to 2 here, as phase reference we have taken as the origin here, right? Okay, in the same way 3 also, if you consider here, e raised to j to psi here. Okay, so on up to n sources here. That's how it has been written here. And at the distance point A in the direction phi, the field from source 2 is always advanced with respect to source 1 here. Remember, the source 2 will be having an advanced what you can say that phase here with respect to 2 phase. Point source 3 will be having a advanced phase with respect to point source 2 here. Okay, so on it will continue to the up to n isotropic point source. These two are the assumptions which you have taken here. Phase reference will be taken from a source 1. Okay, and then whatever the phase is there regarding the second source or third source here, it will be in advance with the previous source here. Okay, these two are the assumptions which you have taken here. Now let us understand and further simplify the equation number 1 here. For a simplification of the 1 here, what we have done here is we are multiplying both LHS and RHS with e raised to j psi here. Okay, if at all we multiply e raised to j psi J psi here on the both LHS and RHS side here, you will be getting this equation number 3 here. So what will be having E capital E into small e raised to J psi is equal to E raised to J psi, so on up to E raised to J n psi here. Okay. Now let us further simplify this particular equation number 3 here. Okay, by dividing 1 minus e raised to J psi here. Okay, right. So first, before doing that one here, we have to subtract the equation number 3 from 1 here. Equation number 1 and equation number 3 is that here. We have to subtract equation number 3, okay, from 1 here. Okay, 1 minus 2 here, and after that we have to divide this 1 minus e raised to J psi here. If at all, let us consider LHS of the equation number 1 and the equation number 3 here. E minus of e raised to J psi here. So what will you get here? You can take the capital E as a common here. Then we can what we can do here is you can just keep as it is. In the same way, the right hand side also we can see here. If at all you 1 minus 3 if you do here, so you'll be having only this first term will be there, and this last term of the equation number 3 will be remaining here. So hence, afterwards you have to divide this 1 minus e raised to J psi here. In the LHS side, you will have only the capital E, and RHS side will be having 1 minus e raised to J n psi divided by 1 minus e J psi here. Okay, so above equation number 4 can be rewritten here. We are just writing here again the simplified manner so that we could bring the total equation in terms of the sign here. Right. So let us take the common as e raised to J n psi by 2 here, and the numerator and the denominator will have certain equation here, e raised to J n psi by 2 minus e raised to minus J n psi by 2, which is in terms of the sin n psi by 2 here. Okay, if you make it divide by 2 here, we have the sin n sin n psi by 2, and here also in the denominator will be having sin psi by 2 here. Okay. Now there is a little bit of modification that we have done to this exponential terms here. So what you have taken is the numerator, denominator thing is taken into the numerator here. Then we are keeping it as a zeta here. Zeta. Now zeta is nothing but here n minus 1 divided by 2 into psi here. Okay. So now if at all equation number 7, we can write in equation number 7 here. Okay. So that is the sin n psi by 2 divided by sin psi by 2 angle of zeta if we consider here. Now, if whatever the phase reference we have taken here, we have taken the phase reference at the initial point here. That is nothing but at the origin of the axis here, right? At the point source 1 here. If at all we consider that the phase reference would be considered center point here. Instead of getting the initial point, let us take it to the center point here. If at all we take the phase reference center point here, then the equation again could be reduced to what you can say E is equal to sin n psi by 2 divided by sin psi by 2. This is the main equation here, final equation here. Okay, so this is how we can get the answer for this linear array of n isotropic point sources of equal amplitude and spacing. If this further this equation number 8 will be utilized in again a broadside array and end side array here. Further we will discuss that one here. Suppose we will consider the total phase difference itself is equal to 0. Then what exactly the maximum value we are going to get here? That is what we have to understand here. So if at all we keep the total phase difference is equal to 0, then the electric field, okay, so is equal to n here. That will be the maximum value the electric field could attain here. Okay. Suppose for example, if at all we consider the E max is equal to n, okay, for normalized value of the normalized value here, then E could be written as E is equal to 1 by n sin n psi by 2 divided by sin psi by 2 here. Okay, this is the equation number 10 here. So remember, equation number 8 is a major one here for linear array of n isotropic point sources of equal amplitude and spacing here. Okay, so let us move on to the next topic, which are very important, which are usually comes into the problem here. Okay, so first one is broadside array here. What is broadside array here? Remember here, what is just definition I'll let you know. You will understand all things when we solve the problem here. So what is an array? Whatever the array is there, linear array is there, no? Is said to be a broadside array if the main beam here, okay, if the main beam is perpendicular to the axis of the array here. Okay, so we have the total phase difference equation, no, psi is equal to dr cos phi plus delta is there here, right? Delta is equal to 0 in the broad side case here. Delta is nothing but here phase difference between the adjacent sources here. This psi is nothing but your total phase difference from all the sources here, right? So here in this case, broadside array case here, what is going to happen? We have to understand that whenever the broadside case comes into picture here, there will be a no phase difference or delta is equal to 0 between the two sources here, okay? Between the two adjacent sources you can consider. So now, if at all I wanted to have that phi is equal to 0, that is total phase difference is equal to 0, or what is exactly the requirement here is phi is equal to 2k plus 1 pi by 2 here. Suppose if at all you are putting the value of k is equal to 0, 1, 2, 3, you will have phi is equal to pi by 2 or phi is equal to 3 pi by 2. Okay, at this particular point here, okay, the field will be maximum. Okay, right? So this is what is broadside array case here. The maximum field is in the direction normal to the array, hence this condition which is characterized by in phase sources, okay, that is delta is equal to 0, that is there is no phase difference at all, results in the broadside array case here. Okay, this is the one first case here. Second case, let us understand, that is end fire case here. Here what is going to happen here is, okay, here whatever the array is there here, no, this will be along the axis of the array here. The previous case was whatever the beam was there or the maximum radiation was there, maximum radiation was perpendicular to the axis of the array. In this end fire array case here, maximum beam will be along the axis of the array here. Okay, that's why it is called as end fire array case here. So in this case here, whatever the total phase difference here, delta is equal to minus dr will be there here. There delta was equal to 0, here it will be having certain phase difference will be there, that is equal to minus dr here. Okay, so that is what is any array where the field is maximum in the direction of the array, that is phi is equal to 0, is called an end fire array case. Okay, these two are the cases here which you have to remember here. Whenever these two cases comes into picture, whenever we try to solve a problem here. Okay, so while solving the problem here, you should remember whenever it has been asked to calculate the broadside array parameters or something else here, so you have to remember that delta is equal to 0, that is phase difference between the adjacent sources is equal to 0. And whenever it has been asked for the end fire array case here, so what you have to do, delta is equal to minus dr, you have to substitute here in the end fire array.